Hello students, so let's explore chapter number 9, hydrocarbon. So this is our theory part 7 and today we are going to cover the section number 9.3 of the NCERT. This is the disclaimer. The learning objective of today's class is that you will be able to understand the structure of alkenes. So we have already dealt with the reactions of alkane, with the structure of alkane and also with the isomerism related to alkanes. Now we will treat the same way our alkenes. If I talk about the specific sections of the NCERT, then we will be covering 9.3, section number 9.3, whose name is alkenes. After that, we will do some questions. So, we will do exercise questions 9.1, 9.14, 9.15 and 9.25. Then after, we will also cover some exemplar questions. So, it is 1, 2, 3 and 10. And lastly, we will summarize today's lecture with a short note. Let us introduce the alkenes. So, alkenes at least contain one carbon-carbon double bond donated by C. Then we have a E is equals to type sign, then C. So, this is representing our double bond and it sets them apart from other hydrocarbons like alkanes. Here we have an image that visually represents the structure of an alkene. Notice the double bond between the carbon. Due to the presence of the double bond, alkenes have two fewer hydrogens compared to alkanes with the same number of carbon atoms. Now this difference is crucial because it affects the molecular formula and the type of reactions your alkene will undergo. Now let us look at the general formula of alkenes finally. So it is CnH2n. This formula helps us to predict the number of hydrogen atoms in an alkene based on the number of carbon atoms it has. It is a handy tool for identifying and working with the different alkenes in a chemical equation, right? Now let us discuss the structure of ethene. Here we have the structural representation of ethene. Notice the double bond between the two carbon atom, which is a defining feature for alkenes like ethene. So this image will help you to visualize the spatial arrangement of atoms. Now let's talk about hybridization, which is crucial for understanding the bonding in ethene. Each carbon atom in the ethene is sp2 hybridized. This means that one s and two p orbitals combine to form three sp2 hybrid orbitals for carbon. This hybridization is what allows the carbon atom to form the planar structure of ethene. In addition to three sp2 hybrid orbital, each carbon atom has one pure or unhybridized p orbital. This unhybridized p orbital is crucial for forming the pi bond in the double bond of ethene, which we will discuss shortly. Now let us focus on the sigma bond in ethene. The CC sigma bond in ethene is formed by the end-on-end overlap of one sp2 hybrid orbital from each carbon atom. You can see it in the diagram. So this overlap creates a strong bond. That is the backbone of the ethene molecule. And each carbon atom also form one CH sigma bond using its remaining sp2 hybrid orbital. So these bonds are formed with hydrogen atom, completing the structure of ethane. So just look at the diagram. All of these things are available there. You can see here that we have two carbon centers and both of them have a sp2 hybridized orbital. Now one sp2 hybridized orbital is doing a head-on-head overlap with the other sp2 hybridized orbital to form a sigma bond. The remaining two hybridized orbital of each carbon will do a head-on-head overlap with the pure s orbital of hydrogen to form the sigma bond with hydrogen. So this is the overall orbital picture for ethene, which is depicting the sigma bond only. Now next, continuing to learn more about the structure of ethane. Here we have an image illustrating the orbital picture of ethane. Notice how the diagram shows the formation of pi bond and the pi cloud. Now this visual is crucial because it helps us see how the electrons are distributed in the molecule, which affects the reactivity and properties. First of all, let us focus on the pi bond in ethene. Pi bond in ethene are formed by the side ways overlap of p orbital. This is different from sigma bond, which are formed by the head-on-head overlap. Understanding this distinction is important because pi bonds are generally weaker and more reactive than sigma bonds. In ethene, the unhybridized p orbital on each carbon atom lies perpendicular to the plane of the sp2 hybrid orbital. This orientation is the key because it helps and allows the p orbital to overlap sideways, forming the pi bond. Next, the sidewise overlap of the p orbital creates a pi bond above and below the plane of the molecule. This arrangement forms a pi cloud, which is a region of high electron density that can interact with the incoming molecules. Right? So this is the overall picture. You can see here it in the diagram as well. So two p orbitals are there, okay, which are unhybridized and they are parallel to each other. Now both of them will overlap sidewise, and after the overlap you will observe a electron cloud which is present above and below the sigma bond. So this is the overall formation of your pi bond. Now we will discuss the bond parameters of ethene. So here we have an image showing the structure of ethene. Notice the arrangement of the atoms and the bonds between them. So this visual will help us to understand the specific bond parameters that we are going to discuss. First of all, starting with the bond lengths. So the carbon-carbon double bond, denoted as C double bond C, has a bond length of 134 picometers. This is shorter than a typical carbon-carbon single bond, which is about 154 picometer. The double bond pulls the carbon atom together. Okay, they are now much more closer as compared to the alkanes carbon-carbon distance. Then the carbon-hydrogen bond, represented as C bond H, has a bond length of now 110 picometer. So this is the typical bond length for CH bonds, reflecting the strong attraction between the carbon and hydrogen. Next, moving on to the bond angles. So the HC double bond C bond angle is approximately 121.7 degrees. So this angle is slightly larger than the typical tetrahedral angle of 109.5 degrees due to the planar structure of the double bond. So when your carbon is moving from sp3 stage to sp2 stage, the bond angle is increasing from 109.5 to 120 degrees. So can you think of a reason why this bond angle has increased? So the reason is your change in hybridization. So when you are changing the hybridization from sp3 to sp2, you are decreasing the p character, which was initially 75% in case of your alkane, and now it is 66% approximately. Due to this decrease in p character, your bond angle has increased. Next, moving on to the bond angle of H, C and H, which is 116.6 degrees. This angle is slightly smaller than the H single bond C double bond C, reflecting the influence of double bonds electron cloud. Understanding these angles helps us to understand the molecule's shape and reactivity. So, continuing with the bond parameters of ethane. Now this was the image. Some part of this has been already discussed. Now we will discuss about the bond strength. What can be said about the bond strength? So the CC bond in ethene is stronger than a C single bond C bond. Specifically, the C double bond C has a bond strength of 681 kJ per mole compared to 348 kJ per mole for a C single bond C bond. Okay, this difference is significant because it affects how ethene reacts with other substances. So it is important to note that the double bond strength isn't simply because of the single bond. This is because the pi bond, which is a part of the double bond, is weaker than the sigma bond. This distinction is key to understand why double bonds are more reactive. So think of it in a way. Basically, the thing which is displayed here is that although your C double bond C is overall stronger than the C single bond C, but if you consider only pi bond, I am considering only one pi bond, then of course it is weaker than the sigma bond of alkane. Therefore, it is more reactive. Okay. So you may think that your C double bond C is stronger, so it will be less reactive. But due to the individual weakness of the pi bond, the alkene is becoming more reactive. Now, moving on to its chemical reactivity, the pi bond in alkenes like ethene provide mobile electrons. So these electrons make alkenes particularly reactive to electrophiles, which are species that seek out electrons. This reactivity is a defining feature of alkenes. Now, alkenes including ethene typically undergo addition reactions, right? So this is the characteristic reaction of your alkenes. Now, let us do a NCERT exercise question 9.1. The question asks, how do you account for the formation of ethane during chlorination of methane? Let us look now let's have a look on the solution. To understand this reaction, we will break it down step by step. The first step is crucial as it sets the stage for entire process. We will explore how the reaction begins and what initiates the transformation of methane into ethane. In the initiation step, the reaction is started by the homolysis of chlorine molecule. This is an important concept because it involves breaking the chlorine molecule into two reactive parts. Let us see how this happens. Chain is initiated by the homolysis by your UV light. Then, during homolysis, the chlorine molecule splits into two chlorine free radicals. These radicals are highly reactive and plays a key role in the subsequent steps of the reaction. Remember, this process requires UV light to provide the energy needed for the bond to break. Here we see the chemical equation representing the homolysis of chlorine. Notice how the chlorine molecule, that is your Cl, single bond Cl, is split into two chlorine radicals, each represented by a dot. This visual representation helps us to understand the formation of this reactive species. Continuing with the solution. So we have seen the initiation part. Now moving on to the propagation. So the second step in this process is called as propagation. This is where the reaction really starts to build momentum. We will see how freely radical plays a crucial role here. In this part of propagation, a chlorine free radical represented as Cl with a dot reacts with methane. So this is an important step because it initiates the chain reaction. Remember, free radicals are highly reactive due to their unpaired electrons. Now, the chlorine radical abstracts the hydrogen atom from methane. This means it takes a hydrogen atom away, which is a key step in breaking the methane molecule. Think of it like pulling out a Jenga tower. Okay, so you must have heard of this Jenga tower. So you are now pulling a block out of this Jenga tower. Now, as a result, we get a methyl radical and hydrochloric acid. The methyl radical is a new reactive species that will continue the chain. This is a classical example of how one electron leads to another in a chain process. Now this newly formed methyl radical reacts with another chlorine molecule. This is the second part of the propagation step where the chain reaction continues to build. It is like passing the baton in a relay race. Then this reaction leads to the formation of chloromethane and generates another chlorine radical. The chlorine radical now can go on to react with more methane, perpetuating the reaction. This regeneration is what makes it a chain reaction. So this was the propagation step. Continuing with the solution. In the step 3, we focus on the termination phase of the reaction. This is where your free reactive, highly reactive radicals come together to form stable products. It is crucial to understand that this step helps in concluding the chain reaction. So, during termination, free radicals combine to form stable molecules. This is an essential step because it prevents the reaction from continuing indefinitely, ensuring that the reaction reaches completion. Various combinations can occur. What are those? One possible combination is a chlorine radical combining with a methyl radical to form chloromethane. represented as CH3Cl. So this is a primary product of the chlorination process and highlights the role of radicals in forming new compounds. Another combination involves chlorine radicals coming together to form the chlorine gas, which is Cl2. Then finally, the 2-methyl radical can combine to form the ethane, which is C2H6. This is the key side reaction that explains the formation of ethane as a byproduct. It is a great example of how unexpected products can arise from radical reactions. So, this is the reaction. You can see here as shown when 2-methyl radical combine, they form the ethane. Now next, to wrap up this, the side reaction explains why the ethane is observed as a byproduct during the chlorination of methane. Now let us do second NCERT question 9.14. The question asks us that in the alkane CH3, CH2C, CH3 twice, CH2, CH, CH3 twice, identify the primary, secondary and tertiary carbon atoms and give the number of hydrogen atoms bonded to each one of these. How you will do it? So let's have a look onto the solution for that. Here is the image that represents the open structure or expanded structure of alkane that is given in your question. Here, beginning with the primary carbon atom. So, the carbon atom which are bonded to only one other carbon atom is recognized as primary carbon atom. So, they have distinct bonding characteristics. Given structure has 5 primary carbon atoms. You can see 1 degree is written on 5 carbons. Each primary carbon atom is bonded to 3 hydrogen atoms. This is a key feature of your primary carbon in alkanes and affects the molecule's chemical properties. So, you can observe that 15 hydrogen atoms are attached to primary carbon present in the given structure. Next, continuing with the solution. So, this was the structure of the compound given in the question. Now, let us discuss the secondary carbon atoms present in the given structure. If you focus on the secondary carbon atom, then these are those carbon atoms which are only bonded to 2 other carbon atoms. Now, these are crucial in determining the molecule's branching and stability. Identifying this will help us understand the molecule's overall structure. So, in this structure, we have 2 secondary carbon atoms. This is important because secondary carbon often plays a key role in chemical reaction due to their position in the molecule. This secondary carbon atoms have a total of 4 hydrogen atoms attached to them. This detail is essential for understanding the molecule's saturation and potential reactivity. Next, continuing with the solution. Here is the structure of the compound that we are dealing with. Now, let us discuss about the tertiary carbon atoms present in the given structure. So, let's start with the tertiary carbon atom which are bonded to 3 other carbon atoms. This is a key characteristic that distinguishes them from primary and secondary carbons. Identifying this helps us to understand the branching in molecule. So, in this structure, we have one and only one tertiary carbon atom. Recognizing this is very important because it affects the molecule stability and reactivity. So, tertiary carbons are often more reactive more stable due to the surrounding carbon atoms. This tertiary carbon atom has only one hydrogen atom attached to it. This is the typical characteristic of a tertiary carbon, and as most of their bonds are with the other carbon atoms. Now, let's move on to the exercise question 9.15. So, the question is asking us that what is the effect of branching on its boiling point in case of alkane. How you will describe it? So, let us have a look on the solution. Effect of branching on the boiling point. So, to answer this question, we need to understand the forces at play. Alkanes experiences intermolecular forces known as van der Waals force. So, these are weak interactions that occurs between the molecules, and they play a crucial role in determining the boiling point. Now let's focus on the straight chain alkanes. So these molecules have a larger surface area, which allows for stronger van der Waals forces to exist. As a result, straight chain alkanes typically have higher boiling point compared to their branched counterparts. So in contrast with alkanes which are branched, we have a reduced surface area. This reduction weakens the van der Waals force, leading to a lower boiling point. It is like trying to stack irregular shaped blocks. They don't fit together as neatly, so they don't hold together as strongly. To summarize, branching in alkanes reduces the surface area, weakens the intermolecular forces, and consequently lowers the boiling point. Moving on to the next question, exercise question 9.25, which says us, why is Wood's reaction not preferred for the preparation of alkanes containing odd number of carbon atoms? Now illustrate your answer by taking one example. How you will solve it? Let us have a look on the solution. So let us begin by highlighting the key points of the Wood's reaction. The reaction is primarily used for synthesizing symmetrical alkanes, which means alkanes with an even number of carbon atoms. This is crucial because it sets the stage for understanding the limitations of the reaction. In Wood's reaction, we use two similar alkyl halides reactants. So this similarity is important because it leads to the formation of symmetrical alkanes. Emphasize that the use of similar reactant is a defining characteristic of this reaction. Okay, so remember this. You can only use two similar alkyl halide as reactant in the case of Wood's reaction, or either you will get a mixture of products. Here is the classical example. So when we have two molecules of bromomethane, they react in presence of sodium and dry ether, then ethane is formed as the product. Along with that, there is a formation of byproduct, that is sodium by sodium bromide, which is NaBr. The key takeaway here is that Wood's reaction results in an alkane with double the number of carbon atom from the original alkyl halide. This doubling effect is why the reaction is limited to produce symmetrical alkanes, reinforcing the earlier point about its limitations. Now moving on further, what we can say for odd carbon alkane. So to prepare an odd carbon alkane, we need two different alkyl halide. This is crucial because using identical alkyl halide won't give us the odd number of carbons which we need. For instance, let us consider using methyl iodide and ethyl iodide. So these are the reaction. Here we see the reaction setup. Methyl iodide react with ethyl iodide in the presence of sodium and dry ether. This should ideally give us propane and odd carbon alkane. However, let us look at what actually happens. Similarly, when two molecules of methyl iodide react in presence of dry ether and sodium ethane, forms along with the byproduct sodium iodide. And similarly, when two molecules of ethyl iodide react in presence of dry ether and sodium butane, forms along with the byproduct sodium iodide. Notice that along with the propane, we also get the ethane and butane as byproduct. This is because the reaction can occur between any of the alkyl halides present, leading to a mixture of product. So this is a key point to remember. So the result is a mixture of alkane, not just a desired odd carbon alkane. So this mixture complicates the process of purification because we don't get a pure product here. It is important to understand that this is a limitation of the Wood's reaction. Another challenge is that boiling point of these alkanes are very close. So it makes it difficult to separate them through simple distillation, which is a common method for purifying liquids. Because of this close boiling point, separation of the alkane become quite challenging. So this is a practical issue that chemists face when using the Wood's reaction for the odd carbon alkanes. In summary, due to the formation of a mixture of alkanes and the difficulty in separating them, the Wood's reaction is not preferred for synthesizing alkanes with an odd number of carbon atoms. This highlights the importance of choosing the right reaction for the desired product. Now, let us practice MCQ from NCERT example. The question asks, arrange the following in decreasing order of their boiling point. So we have option A as N-butane, then B as 2-methylbutane, C as N-pentane, D as 2,2-dimethyl propane. The option are given to us. We have to choose the right option for their decreasing order of boiling point. So how we'll do it? So before that, let me tell you the answer if you know it. So it is option number D. Now let us have a look on the solution. To solve this, we need to consider the factor that affect the boiling point of alkanes. So the first key factor is the molecular mass. Generally, as the molecular mass increases, the boiling point also increases. This is because larger molecules have more surface area, leading to stronger van der Waals forces. Then after, the second factor, which is branching. So for alkanes with same molecular mass, increased branching leads to decrease in boiling point. This happens because branching reduces the surface area available for intermolecular interactions, weakening the van der Waals forces. So with this factor in mind, we can now determine the order of boiling point. For the given compound, the correct order is N-pentane, 2-methyl-butane, N-butane and 2,2-dimethyl propane. Notice how N-pentane with the highest molecular mass and least branching has the highest boiling point. To summarize, remember that both molecular mass and branching significantly influence the boiling point of alkanes. As we seen, N-pentane has the highest boiling point due to its larger size and minimal branching, while 2,2-dimethyl propane has the lowest due to its high degree of branching. Keeping this principle in mind when analyzing similar problem. So what you can say about this whole series, the carbon atom has the same count except the butane, and also the hydrogen atom also has the same count. So basically, with the decrease in branching, the boiling point is increasing from 2,2-dimethyl-butane to 2-methyl-butane and finally to N-pentane. But the N-butane, which has the smallest molecular mass, is in the last, despite it has less branching as compared to 2,2-dimethyl-butane due to having a higher molecular mass in 2,2-dimethyl-butane. Now here comes the second MCQ from NCERT example question, which is question number 2. You have to arrange the halogens F2, Cl2, Br2, I2 in order of their increasing reactivity with alkanes. Options are given to us and we have to give the correct answer. So we have already dealt with this and I have given you this order also. If you remember it, the correct option will be option number A. Now let us have a look on the solution. So this reactions which are given by the given alkanes are substitution reaction, where a hydrogen atom in the alkane is replaced by a halogen atom. This type of reaction is fundamental in organic chemistry as it forms the basis of creating many different compounds. So here is the general reaction formula: Rx plus X2, Rh plus X2 giving us Rx plus Hx. In this equation, Rh represents the alkane, X2 is the halogen, Rx is the halogenated alkane and Hx is the hydrogen halide. This formula shows the transformation that occurs during the reaction. Now, alkanes reacts vigorously with the fluorine F2. This means that the reaction is very fast and often quite exothermic. Fluorine's high reactivity is due to its ability to form strong bonds with the carbon, as they have a high electronegativity difference, making it a very aggressive reactant. The high electronegativity of fluorine accounts for its high reactivity. Electronegativity is a measure of an atom's ability to attract and hold on to electrons. Fluorine is the most electronegative element, which is why it reacts so readily with alkanes. Next, as we move down the halogen group from fluorine to iodine, the electronegativity decreases. This decrease in electronegativity corresponds to a decrease in reactivity. It is important to remember that the less electronegative an element is, the less reactive it tends to be in this type of reactions. So, when it comes to iodine, the reaction with alkanes is very slow and often requires a catalyst to proceed. This is because iodine is less electronegative of the halogens we are considering, making it least reactive in this context. So this is the order of reactivity, right? So basically, the main reason of this order is your difference in electronegativity, which is decreasing from fluorine to iodine. Moving on to the next question. So next is example question 3. The question asks us the increasing order of reduction of alkyl halide with zinc and dilute HCl is given. So you have to determine the correct option for the order? The correct answer is B. And now let us have a look onto the solution. Let us begin by understanding the reduction process of alkyl halides with zinc and HCl. So this reaction is crucial because it helps us to convert alkyl halides into alkanes, which are simpler hydrocarbon. Remember, the goal here is to replace the halogen atom with hydrogens, right? Here it is shown by general reaction when alkyl halide is represented as Rx, which reacts with hydrogen in the presence of zinc and HCl, forming alkane. So let us discuss the size of the halogens. As we move down the group in the periodic table, the size of the halogens increases. This increase in size leads to decrease in the strength of the carbon halogen bond, making it easier to break. Now, with decreased bond strength, the reactivity of the halides increases. This is because the weaker bonds are easier to break, allowing the reaction to proceed more readily. Keep this in mind as it directly affects the order of reduction, right? Finally, let us summarize the increasing order of reduction. So RCl is less reactive than RBr which is less reactive than Ri. So this is the order, and it is due to the decreased bond strength as we move from chlorine to iodine. Remember, weaker bonds are one which leads to higher reactivity, which is why Ri is the most reactive one in this series. Now moving on to next question. You have to decide that which of the following reaction of methane is incomplete combustion. Option are given. So 4 reactions are there. First is in the presence of copper, second is in the presence of molybdenum, third is in the presence of no catalyst, and fourth is also in the presence of no catalyst. How you will do it? So before moving on to the solution, the correct answer is C. Why? So let us reveal the correct answer. The reaction shown here is methane reacting with oxygen to form carbon and hydrogen. This is a classical example of incomplete combustion. Notice how carbon is produced instead of carbon dioxide, indicating that all the carbon atoms are not fully oxidized. So it is occurring due to limited supply of oxygen, first of all, and it results in the formation of carbon blacks. This is important because it can lead to pollution and health issues. Incomplete combustion is less efficient and can be harmful, which is why understanding it is essential. Next, water is also produced as the product. To summarize, the correct option is C. But what about other reactions where your carbon is getting oxidized to carbon monoxide? So those are controlled oxidation, which are occurring in the presence of a metal or a oxide like molybdenum. Okay, let us summarize our today's lecture. So we started from alkenes. So it contains at least one pi bond. So this double bond is what sets them apart from alkanes, which have only single bond. The presence of a double bond affects the chemical properties and reactivity of alkanes, and their general formula is CnH2n. Basically, 2 hydrogens are reduced. I would say they are gone because of an extra bond, which is your pi bond. Then after, we have an example here of the kind of sigma bond formation, which is occurring due to the head-on-head overlap of sp3 hybridized orbital of carbon and the head-on-head overlap of the s orbital of hydrogen and sp3 hybrid orbital of carbon. So what we can say about hybridization in case of sp2, that 1s and 2p orbital are combining to form 3 equivalent sp2 hybrid orbital, where one is doing an head-on-head overlap with another carbon's sp2 hybridized orbital, and the other two are doing an head-on-head overlap with the s orbital of hydrogen. Now each carbon is therefore sp2 hybridized. What about the pi bond? How it is formed? So the pi bond is formed by the side-on-side overlap of the p orbitals, pure p orbitals, right? And they are parallel to each other and perpendicular to each other. No, so they are parallel to each other and lie perpendicular to the plane of sp2 hybrid orbital, and this is what makes their side-on overlap possible. The side-on overlap creates the electron cloud, pi electron cloud above and below the sigma bond. What about the bond length? So the bond length is less, which is 134 picometer as compared to the single carbon-carbon bond, and the CH bond length is 110 picometer. What about the chemical reactivity? The chemical reactivity of alkene is more. Why? Because although the overall strength of the C double bond C is greater than C single bond C, but the individual pi bond is very much reactive due to the presence of a kind of mobile electrons which allows it to do the addition reaction. Okay, so they can act as an electrophile and they can undergo addition reaction forming single bond compound. This was all for today's lecture. Thank you for joining it.